So today we're talking about designing belt drives. Now, as you may be aware, belt drives are very important in the transmission of motion and power. And mainly, you notice that in our field, we have V-belts as well as flat belts. We also have round belts. Sometimes you can also see those that come with teeth and so forth and so on. So that's why the V-belts sometimes are the ones you see. Others, the ones we call timing belts, also coming in for other special applications. But why these are very useful, why belts come in, is that you could need to transmit motion between shafts, between pulleys and like members. Now, what happens during the transmission of motion? You notice that the tension between the two sides of the pulleys, in this case, we have the driver and the driven. So this is the driver pulley, then this is the driven. It is rotating clockwise, meaning that as it pulls this side, the tension on this other side is higher, and we're calling it T1. The tension on the upper side there is lower, and it's T2. So we have the tight side and the loose side, the tight side and the slack side, and hence T1 and T2. So when you decide to do an analysis, you'll notice that moving from the loose side, going towards the tight, in this case, this is our T1 and this is our T2. If we take a small element of the belt, delta X, there are a few things we can pick from there. First, we are going to notice that the angle strapped there is delta theta, and we're analyzing a flat belt. This is a flat belt. Now, the tension is increasing from the low or from the slack side going towards the tight side. When you move by this element, delta X, even your tension is going to increase by delta T. So at this point, we have tension T. As you get to this point, after moving through this elemental length of the belt, delta X, it means your tension will now be T plus delta T. So then what are the parameters we're dealing with? First, we have the angle of lap for the whole belt here, the angle of contact for the belt between the belt and the pulley. This is the angle of contact or the angle of lap. That is the angle we call theta. Then we have the normal reaction, which is as the belt is trying to stick to the pulley because of the tensions, then there is a reaction, which is the force acting away from the pulley. That's the normal reaction. Then we also have the friction force F, which is the product of coefficient of friction and the reaction. Then the coefficient of friction as well. This is between the pulley as well as the belt, between the pulley and the belt. Then, of course, we talked about T1 and T2, where T1 is the high tension, T2 is the lower tension. T1 is the tension on the tight side, T2, the tension on the slack side. V, velocity at which the belt is running, it has to be in meters per second. Now with that, let's apply the condition of equilibrium where we resolve. Resolving in the vertical, rather in this direction, you have here, you are going to have sine and sine. The angle is half, so it's d theta over 2, because this is at the center, and then we start resolving to make a right angle triangle, just like that, because this will be like that, and then like that, meaning it's only going to use half of the angle. So we have, first of all, t plus delta t, then sine d theta over 2 as the angle. The other one is t sine theta over 2. With this, We can also notice that because the angle is very small, sine d theta over 2 is the same as d theta over 2. Sine d theta over 2 becomes the same as that same angle because this is a minute, it's a very small angle we're analyzing on that elemental length of the belt. So that being said, it means this sign falls off. And you remain with t plus delta t in the brackets, then delta theta over 2 plus t delta theta over 2. Next, we can open the brackets. You multiply t by d theta. You have t d theta over 2. Then you also have delta t delta theta over 2 plus t delta theta over 2. Now this and this give us very negligible values. That's one way of analyzing it. And as a result, the whole of this factor, we can basically ignore it because it's highly small compared to these other ones, which will be significant. So with that in mind, it means we just remain with t d theta over 2 plus t d theta over 2. Now, what do you see there? You notice that we can factorize the t. We can factorize the t, and inside the brackets, we're going to have d theta over 2 plus d theta over 2. Now, what is d theta over 2 plus d theta over 2? It's like half plus half. And the answer is just d theta. So t is still standing there. Then you have d theta. That's where we have our equation 3.1. Then let's now, here we were analyzing in that direction. Let's analyze now for the same equilibrium now in the tangential direction, meaning at 90 degrees to the other direction we had to resolve. The only difference is that we had sine, but this time around we have cos. And it's not in the direction of R, but this time it will be in the direction of the friction force. So therefore, we have T plus delta T cos theta over 2 is equal to T cos the theta over 2 plus the friction force. So this is just the newcomer now. Now, all we can do is open those brackets. T multiplied by cos theta becomes T cos theta over 2, cos d theta over 2. Then we have dt, so we have dt cos d theta over 2. Then we have t cos d theta over 2 plus mu r. Now, already you can see this factor and this factor, they are the same. So these can fall out. If they fall out, it means we just remain with what we have on the first part. So mu r is equal to delta t cos d theta over 2. Mu r is equal to delta t cos d theta over 2. Now, assuming that this cos d theta over 2 is equal to 1, meaning the whole of this will have to dissolve. So you have mu r, therefore, is equal to delta t. But if I refer you back to equation 3.1, we said r was representing t delta theta. So in place of r, we put t delta theta. And that being the case, we can now divide both sides by t. So I will say I will divide here by t. Even there, I also divide by t. So here, the t will disappear. But on the other side, I'll remain with delta t over t. Then the other side, I'll have mu multiplied by delta theta. So then I can now integrate between the limits. On this other side, I'm integrating between T1 and T2. The other side, I'm integrating between the angles 0 and theta. Now, what you can notice when we're doing integration is that here I have theta. Sorry about that. My theta doesn't look like a theta. Theta raised to power 0 is what I have here. Theta raised to power 0. And that's what I'm going to integrate. So I will say 0 plus 1 over 0 plus 1. So what happens now? You can see that here I'll end up with theta because I said theta raised to power 0 plus 1 over 0 plus 1 there. And this will leave me with mu theta. On this other side, I have log E or ln E or simply ln T1 over T2. Now I want this to come out nicely so that I can have only T1 over T2 this side. So meaning I'll introduce, it will mean I'll say T1 over T2 is equal to E raised to power mu theta. E raised to power mu theta. Then I'm okay. Moving from logarithms to indices, this is what we've done. Log this is equal to that. Meaning that this number I have here, if I raise E to this power, then I should have this number here from your rules of logarithms. So T1 over T2 is equal to E raised to power mu theta. This is the expression we've been looking for. For a flat belt, the ratio between the tension on the tight side and the tension on the loose side is equal to E raised to power mu theta, where we are saying mu, coefficient of friction, theta, the angle of lap in radians. What about the power transmitted? For the power transmitted, we are going to say it's supposed to be the product of the driving tension and the velocity. The driving tension, which is T1 minus T2. The difference between the tension on the tight side and the tension on the loose side gives us the driving tension. The moment you multiply that by the velocity, you have your power. So if you have been given T1 and T2, there we are. You just substitute and you're good to go. But then it's not always going to be the case. You can make T2 the subject of the formula. And that being the case, it means there, in place of T2, you have T1 over E to power mu theta. But here we've also gone ahead to factorize T1. So then you have, therefore, your power being equal to T1, open brackets, 1 minus 1 over E to power mu theta. The velocity is still outside the brackets. What if you've been given the centrifugal tension? The centrifugal tension, this one comes in for a belt whose mass is not negligible and also running at a speed higher than 20 going up or even 30 going up. So here, centrifugal tension, we say centrifugal force is mv squared r. And then because it's a force we're talking about, then we introduce the theta as well. Then F equals m v squared d theta. So this is supposed to be below there. That is our centrifugal force. So now with that, you see that F is equal to 2 Tc, then d theta over 2. So the 2 here can cancel out, and you remain with your F being equal to Tc d theta. And as a result, you just say Tc, therefore, is equal to mv squared because the thetas will cancel out. So you have Tc is equal to mv squared. For maximum power transmission, the condition is that T, the maximum possible tension, is equal to 3 times the tension, 3 times the centrifugal tension. Then in case you've been given Tc, and there we realize that it's supposed to be you get T1 minus TC, and then you proceed like that, because the centrifugal tension, when it has been provided, you have to take care of it. So going back to the formula for power, in place of T1, you just put this. That maximum possible tension minus TC. Then everything here remains the way it was at first. For V belts, we just introduce one factor here, which is just T1 over T2 is equal to E power mu theta. Then we also put in cosec beta over 2. Cosec beta over 2. Let's apply. So here we have a question. Our question is saying the flat belt, the cross section is 100 by 5. Material of the section density is 900 kg per cubic meter. The belt is used to transmit power to a pulley whose angle of lap is 150 degrees. Coefficient of friction between the belt and the pulley, 0.25. Maximum stress in the material of the belt, 2 newtons per square millimeter. Speed of the belt, 30 meters per second. Let's calculate, or we are required to determine the power transmitted, the maximum power, and the power transmitted, suppose this is the V belt and the groove angle is 32 degrees. The data provided, the area of the belt, what we were told is that the cross section of the belt, meaning looking at the belt's cross section, of course, the length of the belt can continue like that. It hasn't been given, but when you look at the cross section, this, we've been told it is 100 in the length or the width, then the thickness is 5 millimeters, meaning that the cross-section area therefore becomes 500 square millimeters. Density, 900 kg per cubic meter. The stress, 2 newtons per square millimeter. Coefficient of friction, 0.25. Velocity of the belt is 30 meters per second. Then let's find the mass per unit length of the belt. So this is supposed to be density times the area. Density multiplied by the area. The density is 900 kg per cubic meter. We cannot use this area in square millimeters. We have to convert it to square meters. Converting to square meters, we divide by 1,000 squared. So 500 divided by 1,000 squared. Our answer, when we multiply by 900, we get 0.45 kg per meter. Because we're talking about the length per unit, rather the mass per meter, mass per unit length. The angle of lap is 150 degrees. The only problem it has is that it's in degrees. So we have to convert it to radians. So we have 150 times pi over 180, giving us 2.618 radians. Now, with that in mind, all right, it's just some highlights. Power transmitted. First thing we're going to do, find the maximum possible tension T. So we multiply stress by area. Stress was 2 newtons per square millimeter. The area was 500 square millimeters. So the units are talking to each other. They'll cancel each other nicely. Meaning our answer, therefore, is 1,000 newtons. Centrifugal tension, TC, we said it's mv squared. mv squared. So 0.45 times 30 squared, which is equal to 405. Then we can get our power. Power is T, maximum possible tension, minus TC, open brackets 1 minus 1 over E power mu theta, then outside the brackets, velocity. So let's substitute. Our T is 1000, centrifugal tension 405. Then we have 1 minus 1 over e to power 0.25 times 2.618. Multiply everything by 30. So there, our answer from here, when we subtract these two, we get 595. In between here, we get 0.4803. Then we bring down the 30. Then our power is 8,573.355 watts. Maximum power transmitted. We need to recalculate TC because what condition do we need to transmit maximum power? T is equal to 3 times centrifugal tension. So therefore, T is 1000. Divide by 3, we get 333.333 newtons. Then we also need the maximum velocity. Vmax is also coming from this. So T is equal to 3mv squared. You say Vmax is equal to T over 3m, which is 1000 over 3 times that, giving us 27.216. This is the velocity at which maximum power will be transmitted for this belt material, for this belt. So with that, we can now go ahead and substitute. We have T minus TC, open brackets, 1 minus 1 over e to power mu theta. Then here we put Vmax. Vmax. So T is 1000, TC is 333.333, 333.333. Then open brackets, 1 minus 1 over e to power 0.25 times 2.618. We're multiplying by 27.216. Again, this is the 666.667 times. In between here, it's the same 0.4803. Then on the other side, the 27 comes down. And hence, our maximum power comes out as 8,714.568 watts. Now, suppose this is a V belt. If this is a V belt, then we're saying power is T minus TC in the brackets. Open brackets, we have 1 minus 1 over E raised to power mu theta. Then this is the only addition. Cosec beta over 2. Cosec is the same as 1 over sine. So meaning if you want, you can introduce that as 1 over sine at that angle. Then there's V. Angle beta has been given as 32 degrees. So we keep that in mind. Meaning 32 divided by 2, you can even plant the 16 there. You can even put the 16 degrees there as you do the substitution. Or you leave it like that. Then it will still be 32 over 2, coming back to the same number. So 1000 minus, this is 405. Inside we have 1 minus 1 over e to power 0.25 times 2.618 cosec 32 over 2, which is going to 16. Then the velocity of this belt is 30 meters per second. With all that, here, our product this time around is coming to 0.9069. Then our answer is 16,188.856 watts. Here is the reality. When you're dealing with a V belt, the power transmitted is higher. You can understand why using this type of a belt when we're transmitting, in most of those transmission systems where we need maximum power to be sorted out. So the power transmitted, therefore, is 16,188.856. As usual, you have an exercise there for you to try out, and the answers are already there. Clarity, where you need to clarify, please reach out, put a comment in the comment section, and we'll definitely find time to quickly get back.